Hello, welcome to the second video about the resolution of linear system using the Gauss algorithm. So this video is related to the previous one, so let me recall you what the previous one was. The previous video, the title is Linear Systems Gauss Algorithm 1. You can still find on the Mati project YouTube list of videos, and in that video we were whose aim of the previous video was to solve a linear system by transforming it into an upper triangular one. And as we saw, we could use the Gauss algorithm to make some transformations and to transform the linear system into an upper triangular one, which is equivalent to the one we started with, but which is easier to solve. The aim of this video is, instead of transforming the linear system into an upper triangular one and then solving it, we want to transform the linear system into a diagonal one and then solving it. But a diagonal linear system is much easier to solve than a diagonal one. An upper triangular one. So I'm going to show you this by the means of the same example I used in the last video, so the result will clearly be the same. And so I recall you what the example is. So we had the following linear system, which is again a linear system of three equations in three variables x, y, and z. The first equation is x plus y plus z equal 1. The second equation was minus x plus y minus 2z equals 0. And the last equation was 2x minus 3y plus z equal 2. And so today's aim is to solve this linear system by transforming it into a diagonal one. And again, we are going to make use of the same transformations which are the core of the Gauss algorithm to transform this linear system into a diagonal one, which is equivalent to the one we started with, and so they have the same solutions. But the diagonal linear system is going to be much easier to resolve than the one we started with, so somehow we simplify the problem. So I recall you what the transformations are. So you may find these transformations even in the previous video. So the first kind of transformation is given by a sum of two rows. This means that we may replace a row by the row itself plus a multiple of another row. The second transformation is the multiplication of a row by a scalar, and we have to suppose that the scalar is not 0. And the third transformation is switch two rows. So let me show you how this example. Let me show you this on the example I wrote before. So exactly as in the last time, what we do is that we take the matrix of the coefficients of the equations. So the first column of the matrix is given by the coefficients of x, so 1, minus 1, and 2. The second column is the coefficients of y, so 1, 1, minus 3. The third column is the coefficients of z, so 1, minus 2, 1. And the last column, which is separated from the three we just wrote is the column of the right, given by the right-hand side of the linear system. And so the idea is that we want to transform the matrix you have here on the left-hand side of the matrix into a diagonal one. And so the problem is that here we have this part here, which is not 0, and this part here, which is not 0. So the matrix is not yet diagonal, and what we need to do is to use the previous transformations to transform this matrix into a diagonal one. And so the idea is that we start by, for example, using this 1 here in order to let disappear the 1 and the 2 you have here. So we transform them into zeros. And we do exactly the same kind of transformations we did last time in the last video. So the idea is that we replace the second row by the second row plus the first row. In this way, the -1 becomes -1 plus 1, which gets a 0. And the last row, we subtract twice the first row. And exactly as in the last video, we get the first line remains the same, the second line gets 0, 2, -1, 1, and the last row is 0, -5, then you have 1 minus 2, which is -1, and 2 minus 2, which is 0. So again, this matrix here is not yet diagonal, because here we have this -5, and here we have this 1, 1, and -1, which prevent the matrix to be diagonal. So what do we do now? Well, the idea is that we may use the 2 we have here to now modify this 1 here until it becomes 0, and this -5 here until it becomes 0. So what do? We use the same kind of transformations, but now this is the main difference with what we did last time, because last time we just transformed this -5, into a 0, and to do that we used twice the last row plus 5 times the second row, and this will let this -5 times 2 gets -10, and then you add 5 times 2, which is 10, so you have -10 plus 10, which gives you a 0. But now the main difference with respect to what we did last time is that now we want to let become this 1 is 0. And so in order to do that, what we do is that you take twice the first row, and then you subtract the second row. So once you do this, the matrix you get has the same second row as before, so 0, 2, -1, 1. Now the last row becomes a 0, here you have a 0, then you have -2, -5, which is -7, and here you have a 5. But instead of stopping here exactly as we did last time, now we take twice the first row and we subtract the second row. So you get here in the first entry of the first row is 1 times 2, which gives you a 2, minus 0, and you get 2. Then you get 1 times 2, which is a 2, and you take out a 2, so you get a 0. And then you have 1 plus 2, which is 2, and then you take out -1, so you get 3. And then you have 1 times 2, which is 2, and you take out 1, and you get a 1. So this is the new matrix you get. Now the point is that the matrix again is not yet diagonal, because here you have this 3 and this -1, which need to become zeros. And so we may again use the same kind of transformations as before, but now the only entry we are allowed to use is this -7 here. So how do we use it? Well, the main transformation you can do is that you may take 7 times the first row and you add the last row, and here you take 7 times the second row, and then you take out the last row. Sorry, I'm so sorry, this is not plus. Yeah, so you take 1. In this way you get 7 times 3, which is 21, and then you need to subtract 21, so you just need to sum up 3 times the third row. So once you do this, what you see, the last row remains the same. For the first row, you multiply this by 7, and so you get 2 times 7, which is 14, minus 0. This gives you 14. Then you have 7 times 0, and then you subtract, you add 0, so you get a 0, and then here you get a 0. And then you have 7 times 1, which is 7, and you are adding 15. So 7 plus 15, it gives you a 22. For the second row, here you have a 0. Here you have 2 times 7, which is 14, minus 0. This gives you 14. Then you get minus 7 plus 7. This gives you a 0. And here you get 7 times 1, which is 7, minus 5. It gives you a 2. So here is the new matrix we get. Now, to this matrix correspond a linear system, which is now very easy to write down because it is 14 times x equals 22, 14 times y equals 2, and minus 7 times z equals 5. But this is a linear system which is immediate to resolve, because from this you get that x is 22 over 14, which is, by simplifying this fraction, it is 11 over 7. Y is 2 over 14, which is, by simplifying it, 1 over 7. And z, it is minus 5 over 7, which doesn't need to be simplified. And so, as a conclusion, the linear system has a unique solution, which is, as we expected, 11 over 7, 1 over 7, minus 5 over 7. And this concludes the strategy. So, as you see, we just pushed the Gauss algorithm to the extreme consequences of it. So somehow, instead of just transforming the linear system into an upper triangle, the matrix into an upper triangular one, we transformed it into a diagonal one, and this gave the answer in an easier way. The only thing is that we need some more steps to complete the Gauss algorithm.